This is how a positive charge will move in a magnetic field. In order to use one plane to sketch three directions, we use this notation. This X means that the direction of the B field is going into the screen. On the other hand, we use dot to tell us that the direction is coming out of the screen. So the field can be into the screen or out of the screen. If it is into the screen, it will be represented by these X's. If it is out of the screen, it will be represented by dots. So here, if you consider a charge, positive charge Q entering this field, when you apply the right-hand rule, your four fingers representing this direction, and the field is into the screen. So when you curl the four fingers, the thumb will point upward. So this will be the direction of the force. The acceleration will follow the direction of the force. So the acceleration, which is the change in the velocity, will be going this way, and as a result, the velocity will change its direction, and at any moment, the same story repeats. Always the acceleration is perpendicular to the original direction of the velocity, and as a result, the charged particle will move in a circular orbit. It will be circular motion. So the magnetic force acting on a positive charge particle in a field going into the screen will be always directed toward the center, as in this drawing. Recall that force equals ma from Newton's second law, and for circular motion, A is v squared over r, v squared over r. So we have mv squared over r equals qvb. Sine theta, in this case, theta is 90 degrees. The direction between v and b is 90 degrees. Sine of 90 is 1. So we have qvb equals mv squared over r. We can solve this equation for r. It is equal to mv divided by qb. So the radius of the circular orbit is governed by this equation. It is always equal to mv, the momentum, divided by qb. qb is called the magnetic rigidity. Magnetic rigidity. Each particle has its own magnetic rigidity in a magnetic field. If the initial direction of the velocity is not perpendicular to the magnetic field, then we can decompose it into two components, one perpendicular to the field and the other parallel to the field. The one perpendicular to the field will create the circular motion, and the one parallel to the direction of the field will make the circle into a spiral like this. So the charged particle will follow this spiral path in that case, when the initial direction is not perpendicular to the magnetic field. We call this a helical path. So the path will be circular, closed circle like this, only when the direction of V, the initial direction of V, is perpendicular to the direction of the magnetic field. If it is not perpendicular, then we will decompose it into parallel and perpendicular components, and the outcome will be helical path like this. As a charged particle moves freely in a circular path in the presence of a constant magnetic field applied perpendicular to the particle's velocity, the particle's kinetic energy, we have three suggestions: remains constant, increases, decreases. Recall that the kinetic energy is equal half mv squared, and the magnitude of v does not change because the acceleration is always perpendicular to the direction of the velocity. So it will not change the magnitude of the velocity, and because of that, the kinetic energy remains constant. This is when the magnetic field is going out of the page or out of the screen. For a charged particle entering into this field, when you apply the right-hand rule, this will be the possible path for the particle. So here, this is the direction of V, the four fingers pointing this way. The field is out of the screen or page. When you curl the four fingers from this direction toward the out direction, then the thumb will point this way. That will be the direction of the magnetic force. One nice example of this behavior of charges as they enter into magnetic field is the mass spectrometer. Mass spectrometer is very important in both physics and chemistry. It allows us to measure masses of isotopes, to separate isotopes from each other. Isotopes are very close in mass to each other. Like you have carbon 12, carbon 14, you have chlorine 15, chlorine 17, you have uranium 238, uranium 235. So always we are interested in separating isotopes to measure the abundance of various isotopes in nature. In this example, we are told that two singly ionized atoms move out of a slit at point S, at this point here, into a magnetic field of 0.1 Tesla pointing into the page. The field is pointing into the page. Each has a speed of 1 by 10 to the power 6 meter per second. The nucleus of the first atom contains one proton and has a mass of 1.67 by 10 to the minus 27 kilogram. This is the mass of the proton. Whereas the nucleus of the second atom contains a proton and a neutron and has a mass of 3.34 by 10 to the minus 27 kilogram. This is deuterium. So these are the two isotopes of the hydrogen. The first one is the ordinary hydrogen, the other is deuterium. Atoms with the same number of protons in the nucleus but different masses are called isotopes. This is what we know from chemistry and physics. The two isotopes here are hydrogen and deuterium. Find their distance of separation when they strike a photographic plate. So here we have a photographic plate. The two ions enter into this field, and because of the magnetic force, the trajectory will follow these circular paths. The radius will depend on mv divided by qb. So in this case, for the first isotope, R1 is m1v divided by qb. This is m1, this is the velocity, this is q, this is b. So R1 is 0.104 meter. Then for R2, it is m2v divided by qb. So here we have the mass for the second atom multiplied by v divided by qb. The radius is 0.209. The difference between the two paths is equal to the difference between 2r2 and 2r1. We are interested in the diameter. Diameter is equal to twice the radius. So the difference is equal to 2r2 minus 2r1, which is 0.21 meter.